Hello, everybody. I'm Marc Colley, software engineer in a physics laboratory in Sorbonne University in Paris. We start this morning with Python and CuPy library. You can find the course, the presentation on the God's Code package. I put the link in Discord. So go to GPU, tutorial, and Python GPU CuPy. So CuPy appeared in 2013. The goal of CuPy project is to provide Python user GPU acceleration capabilities without in-depth knowledge of underlying GPU technologies. The CuPy team focus on provide a complete NumPy, CuPy API coverage to become a full drop-in replacement, as well as advanced CUDA feature to maximize the performance. And it's a mature and quality library as a fundamental package for all projects in need acceleration, from a lab environment to the large-scale cluster. So CuPy use GPU backend GPU NVIDIA, like cuPlus, cuRun, cuSolver, and so on. For AMD GPU, CuPy have an experimental support with ROC version 5, with also some limitation, like features specific to CUDA. Here you have a speedup of NumPy. So here the speedup is in a log scale with two sizes of array. As you can see, small data result in less gain. Type of processing with element-wise operation brings the best gain. You can see there can be a factor of 10 between the speedup of complex operation, like matrix multiplication, and element-wise operation. In fact, a matrix multiplication vector must combine elements distant in memory, and the acceleration not increase with the size of the matrix. And after we have memory management. So we define device and host memory. The term device is used to designate the GPU, and host is used to designate the CPU. And we are moving towards the architecture where GPU and GPU use shared memory with new NVIDIA Grace Hopper superchip. So a NumPy array is obviously stored in a host memory linked with the GPU, and CUDA ND array is stored in a device memory. All array allocation is done on a current device for CuPy ND array. So you import CuPy, you define a simple array, and you can ask you have an attribute with this array device, and it returns the name of the device. So for CuPy array is always CUDA. For memory transfer, why two kind of transfer, host to device, H2D. So to do that, you define a NumPy array, and to put it in GPU, you use the method asArray of CuPy ND array. So this line move the memory to host to device. Now device to host. CuPy array has a method get to do that. So you can define an array directly in a GPU memory, and you can transfer it in GPU with get method. It's very simple. Another method is to define is to use a method as NumPy from a NumPy array, and the parameters is a GPU array. So warning about the cost of transfer between GPU and CPU. Small different count transfer penalize performance, and a good memory usage and transfer are the key of a good GPU performance. So we have a dedicated transfer with pinned memory. Pinned memory, also known as a page lock memory, provide a significant performance benefit for the host device transfer. Pinned memory allocation is done by a CuPy specific function. And for transfer device to host, host to device, is performed with NumPy mode function, not with get method. So we see the allocation. So the allocation function is in library CuPy CUDA, and call function allocated pinned memory with the size. And you need to initialize your NumPy array with this return value. So you have an example. So here I define a big array. I ask the memory on the CPU with the CuPy method alloc pin memory, and to create my NumPy array on CPU, I call the method from buffer with the return of the function alloc pinned memory with the kind of with the type and the number of elements. So with this NumPy array, the transfer will be fast. CuPy provide more friendly function to define the pinned memory with in library CuPyX. We have 4 functions: empty-pinned, empty-like-pinned, zero-pinned, zero-like-pinned. So see the CuPy documentation here. So now we will see the transfer with the pinned memory. So you create an array on a GPU with a random value. And to transfer this data in a CPU, you call memcopy function in a library CuPy CUDA runtime. It's the same argument I NumPy copy in C with a destination, source, size of element, and the last parameter is the kind of transfer, device to host, host to device. There are an asynchronous version of memcopy with additional parameter stream. It's called memcopy async, async. Voilà. So now we will see the coverage of version of NumPy, CuPy of CuPy. So the first object is the CuPy array. All routine of NumPy and CuPy from CuPy apply on this object, CuPy and the array. CuPy and the array is very similar to NumPy and the array. The same attribute and more. You have, for example, device contains the ID of the device where the array is stored. You have some method, with a few exceptions. For example, the resize method is not available. And you have a new method, get, to transfer data from a GPU. There are some feature with slicing. There are some difference between CuPy array and CuPy array and NumPy array. But you can also use broadcasting. And another difference is it's with CuPy arrays, float 128 is not available. If you are lost in your code, if you want to know which kind of array you have, you can use this instruction to know if your array is a CuPy array or NumPy array. So this instance, the name of the variable, and CP and the array, it's a class. So here, X GPU is really a CuPy and the array. So now we will see the coverage of NumPy function in CuPy. The documentation provides a table for comparison with 2 columns, NumPy and CuPy. As we see, the coverage is very good. And sometimes in the function is available, but some parameters is not exactly the same. So you need to read the document, the CuPy documentation to know exactly the parameter available in CuPy. Here you have a page with some difference between CuPy and NumPy. Let you read it later. There are some difference for random method. CuPy supports a dtype argument in a random function, and NumPy not always float 64. And another difference, structure array and record array are currently unsupported in CuPy. So you have only the basic object in the array and not the object with, you can define column, a collection of columns. So first example of processing on GPU. You import CUDA, you import CuPy library and you define a function with a version of CuPy function operation. So CuPy sum, CuPy square root. So you create an array on GPU, call the function, and the execution is performed on a GPU. It's very simple. Benchmarks tool. CuPy provides a useful utility. CuPy profiler benchmark to time in the elapsed time of the Python function in both CPU and GPU. So you can import this benchmark with this line. And to call it, the first argument is your name of your function. The second is the parameter of the function. And like in timing function, you have a number of repeats. There are other parameters. And the result, you have two timing, one timing on CPU and another one on the GPU. It's very important to use this function because the return of Python timeit is not precise. To see the difference of computing between GPU and CPU, you can write a CPU version of the previous function. Square root of sum of square element. And as you can see, it's a NumPy version. And with the timeit, we have 4 milliseconds for CPU and 300 microseconds for GPU. So the speed up for this function is 10. CuPy provides also a CPy function. So as a NumPy function, you have a table of comparison. That variable in the documentation. So as you can see, the coverage is also some good. The best coverage is for multidimensional image processing, and the worst coverage is for statistical function. So if you want to do a statistic with GPU and CuPy, maybe it's not a good library. So the important point is CuPy array is very close to NumPy array. The conversion between CuPy NumPy array cause a physical transfer between GPU, CPU memory. And CuPy version of NumPy and CuPy function are processing on GPU. Now, we will talk about the user kernel. maybe you can write all your code with NumPy and CuPy. You must define a specific function. And CuPy accepts a user kernel. There are different kinds of kernel. We represent three. The first is a raw kernel. It's like a C CUDA. Raw kernel object allow you to call the kernel with CUDA launch kernel interface. In other words, you have control over write size, block size, memory, shared memory size, and stream. So here you have an example. So the kernel is defined in string, the triple quote here. Here you recognize C language. The return is the name of kernel. The return of function is the name of kernel. So to the first call, CuPy will compile this kernel in CUDA to execute it on GPU. So for this example, it's a simple addition between a two array. So here is a line where you call your kernel. And the first argument are the grade and block argument and parameters. And the last parameter is the parameter of your function. So the two input array and output array. Another kernel very close of raw kernel. It's a JIT raw kernel. It's the same thing with Python syntax. So you import JIT function from CuPyX. You write a Python code, not a string this time, but with the syntax of CUDA API, and you add a decorator, JIT raw kernel. For this function, it's simple copy with two arrays. So to test it, you define an array X in input, an empty array in output. You call your user kernel with JIT raw kernel decorator. You define block and grade and the parameters of your function. And you test if the copy is really done with this syntax. Another kind of kernel is kernel fuse. So CuPy provides a decorator, CuPy fuse. with this decorator, you can use function element-wise and reduction kernel. Is very close to the Python code. Here you have an example. So the difference with the previous kernel, you don't have this line close to the CUDA definition of kernel. It's like a Python function. So you just need add decorator at the top of the function, and eventually define a name of the kernel. But by default, the name of the kernel is the name of the function. So it's a Pythonic kernel definition with CuPy. So the limitation of this kernel, it's only element-wise. For example, you cannot do multiplication, matrix multiplication. You can do reshape of array. And with this kind of kernel, you can't control grid size and block size, share memory. It's automatically defined by CuPy library. So now a little introduction to the concurrent processing. Parallel execution of different processing is possible with CUDA GPU. It's a notion of stream, an equivalent of thread for CPU. Remember, thread have another meaning in a GPU domain. The creation and use of stream is easy with CuPy. See this example. We create two streams, A and B, to execute in parallel. And at the end, we will merge their outputs. So we start to import CuPy. We define two streams, A and B, from library CuPy CUDA. So it's an object. We define two arrays on GPU. It's a very example without processing. And to start a stream, you use a Python function with. It's a context. And all code under this with are in stream A. So by default, if you define two streams like this, CuPy create two streams of processing on GPU. It's, for example, you define between the two streams stream A synchronize, the program become sequential. So the stream execute, wait to the end, and launch the second stream B. So to have a parallel execution, don't use synchronize between the two streams. So here, after the definition of the two streams, normally A and B are running in parallel, and you wait at the end of the processing to do the final processing. So to wait the end of a stream, you call the function synchronize A, synchronize B, and you call your function to have the final result. At least two constraints to execute a stream in parallel. The GPU has enough resources for the both processing, and processing should be not too short. In principle, stream A and B do different things. The typical example on the GPU, it's a memory transfer and kernel execution with, for example, the technique of double buffer. So here, an example of double buffer. Une question sur... I don't have Discord online.
So we have Luca on Discord who asks, can these GPU streams be across multiple GPUs? Problem 5 in CuPy lectures.
Can you repeat, please?
Can these GPU streams be across multiple GPUs? Problem 5 in CuPy lectures.
Multi-GPU?
Yeah, can these GPU streams be across multiple GPUs?
So here, a stream is only on one GPU. Maybe I ask on the question at the end of the presentation on Discord. Sorry.
Yeah, okay.
So an example of a double buffer with CuPy library. So we define a processing where the I/O is where the processing is I/O bound. So yeah, much I/O data transfer than CPU GPU processing. So you start to define a big array. We create two buffers on GPU and CPU also. So the goal is to transfer GPU buffer in CPU buffer. You define two streams. And the stream with write attentively on two buffer. The process writes its result on one during the other is transferred to the CPU. And the process cannot write until the transfer is not complete. So we need to use synchronize. So we will iterate on these two transfer. We iterate on these two streams with a simple loop. In this loop, you launch the stream, the stream 0, 1. So you do your processing. So the processing is very simple. You create a CuPy array. You compute the signers of the value, and you do the transfer with get method. And to use this stream, you need to synchronize it. So the first loop, you can launch your stream. This test is not performed. Second loop, you can launch your second stream. But launch the stream 0, you need to synchronize it. You need to wait that the transfer has done. So one stream compute and another one transfer. So I propose you an exercise. The exercise is to write a version of this function with pained memory and compare the timing with profile benchmark. So the use of pinned memory, we see it at the beginning of the presentation. So you must use a dedicated allocation for pinned memory. And you must use a dedicated function for the transfer with num and copy. I propose use a solution. So the difference with the previous version is this line. You create a CPU buffer with CuPy X empty pin function. And the second modification is replace get method by memcopy here. Where the first parameter is a CPU buffer. And you go to the device to host. So I do the timing on NVIDIA A100. For the classic NumPy array, the timing is around one second. And for the version with pinned memory, it's 0.3 seconds. So the speed up is 3. Between the two versions. So it's the use of pinned memory is very efficient. And you must use it for the I/O bound processing. Now we can start the implementation of Grayscott equation. So some word of the scope of the course of Python GPU. So the use of raw kernel is covered by other language, C++, in Grayscott school. And in this course, we will only examine kernel fusion and the use of CuPy version of NumPy and CuPy function. However, keep in mind that it's possible to have a control over write, block, size memory, and stream with CuPy, and also stream synchronization, event, and so on. I will define the Grace Code bench. So what you must do, what's the constraints for the Grace Code bench. So the constraint is use a stencil free with -8 at center and 1 all around. We must provide an image in full high definition in a float 42. You must keep one image every 22 iteration, and write HDF5 file with 1000 image in float 32. And the end of the bench is when the HDF5 file is written. So we have four steps: processing the Laplacian, update time with kernel fusion, answer step 1 and 2 in loop, and manage all images and write it in file. Each step is in fact an exercise. So the first, processing the Laplacian. So we will write the 2D convolution between array image and Laplacian stencil with convol 2D function from CuPy, CuPy signal module. So I propose you to write a very short line. To do that, not necessary and executable for GPU. So the solution is here. So you import CuPy. You import convol 2D from CuPy CuPy signal module. You define your stencil on GPU with CuPy array. You define it with this type, float 22. And to do the convolution, you call so the convol function 2D. So with an image, with the stencil, and to manage the boundary, you ask to have an array with the same shape in return function, and you fill the border with 0. So with this code, you perform your Laplacian on GPU. So I think the parameters are exactly the same as CPU function. So there are no modifications to call this function between the version of NumPy and CuPy. Step 2, we must write the kernel with update time. It's a global equation of Grace Code. So I'll let you some minutes to do that. So the solution is very simple. We import the CuPy. You define your function, kernel, Rails code kernel. And it looks like NumPy version. I think there are no difference between NumPy version and CuPy version. As we see, you don't have a return value. The processing is performed in place. So it's quite very easy. So now step 3. You must insert the previous step in a nested loop and store the result in a CuPy array. So for each 22 iteration, and you process by a chunk of image. We don't transfer image by image during processing. We are fill a buffer with a chunk of image before to transfer it in CPU. So you must do these two loops. And the output of this is frame V. It's a CuPy array on a GPU memory. Solution. So we start to create this frames V on GPU with a good shape. So the number of chunk and the number of row and column. We have two loops. One over the number of chunk, and another one on the number of iteration, so 32, 32, sorry, 42. And in this loop, you have the one step of the resolution of with a finite difference of the Grace code equation. So you start to compute Laplacian of U and V, and call the Grace code kernel with this Laplacian. So the results are in place in a V GPU variable, and so every 32 iteration, you write an image in your output buffer frames V. To fill your chunk of image. The last step is almost on the CPU side. You must manage the number of chunk. You must cut the processing by chunk and write processing by chunk, retrieve the chunk from GPU, and write it on file. Solution. So this is the function to write. So in fact, in fact, is it's short. We start to define stencil on a GPU. You transfer initial array provided by the initial function on GPU with as array. So here you transfer NumPy array to CuPy array. So the image at the beginning are on the GPU memory. Here you define your chunk of images. Here is a subfunction with the grayscale resolution for chunk of image with the to loop. And here you have a block of code to manage the output file. You start to create a HDF5 file. You must define at the beginning the size of this file with the total number of images, so 1000, and the full HD dimension of the image, and specify the type of the array in file. Another thing you must do, you must manage the processing by chunk and manage the last chunk, and it can be smaller than the first. So you call your CuPy grayscale resolution in GPU. So this function is blocked. When it's finished, you can write the result frame V on file. So with the transfer is performed with the get method, and this initialization performs the write on the disk. So it's very short. You have on the GitLab of the grayscale Python package, you can find the solution in GPU solution and grayscale CuPy solution. If you want to launch it on your data center or laptop. So the version, you have two versions. You can use this one. Here you have a main. Oops. With the call of initialization and and call the function with a time int. And the last line is to do the movie. So for the user of a data center of this laboratory must. You can follow this tutorial. Yes, it's here. You can clone this package. To use the data center, you must define a free file. One for the scheduler, HD Condor. Another one to define the upturner parameters. And the last one is the Python script you want to process. So these three scripts are defined in a cluster directory. So the first is Grayscott Python submit. You ask for resources on a data center. So here you can see you ask GPU, one GPU, and the kind of GPU. The first line call the script to execute. So for upturner, it's this line script upturner run. So you must define where you can find the image of your upturner and the directory where you clone your Grayscott Python package. In prefix, so you must add that this variable and run upturner. You have some parameters. NV is specific for NVIDIA. You must define CUDA directory in your upturner. So you bind this directory in your system file in upturner. So here is your image, upturner image. And here the script to execute in upturner. So it's a last script. The last script is a script inside upturner. So you must define, you must add CUDA directory in your path and LDA library path. And after that, you can run your Python script. So for the Grayscott Jack solution, you must run in a directory in the directory. So you must do a change directory before. After that, you can submit your script, your job. With the first script is Grayscott Python submit, and you can check the status of job with Condor query. Maybe this afternoon we have more time to do that. Not necessary with the CuPy version. So now we can examine the performance of the implementation. So we will use NVIDIA profiler inside. So to call this profiler, you must prefix your line command nsys profile and Python in your script. At the end of the process, at the end of the job, you have a report, and you can examine this report with a GUI, the nsys-UE. This GUI, you can install it on your personal computer. It's not a problem if you don't have a GPU on your laptop or machine. The only constraint is you must use the same version of GUI as the profiler on the data center. So in this link, you have all version. So you must use this application inside system. So for most, you must use this version. So the first profiling. So here you have the line of GPU with two lines. The first is for kernel, the second is for memory. So here you see the iteration of Grayscott kernel. So for the number of chunks. And at the end, you have the transfer memory. For this version of Python, the CPU takes the end and write the file on disk. And at the end, restart processing on GPU, and so on. So during writing to the disk, the GPU do nothing. And this writing must be parallelized. We have seen that Python thread is not efficient for calculation because of the GUIL, Global Interpreter Lock. But for I/O disk access, they are usable because threads are waiting for the system function. So exercise, write with the thread library of Python a parallelized version to write on the disk. And this solution takes about 20 seconds on A100 NVIDIA card. The solution. So we will go to the main loop on the chunk. After simulate chunk on GPU, you create a thread To create a thread, you must define a target function. So it's a create function write HDF5, this one. The argument of this function must be packed in one variable, so it's a tuple. So the first argument is a file description of HDF5 file description, the index of the first where you write your array. And here you have the transfer function GPU to CPU. So it's a thread definition. You must activate this thread with a start method, and the execution of the thread is not blockant, it's concurrent. So the loop can continue. You must manage all the threads, so you can create a list of threads and add the value of creation of the thread. And at the end, you must wait at the end of all threads. So with the Python library, it's a join function. And the last instruction is close your HDF file with close function. So the profiling is now the profiling is a change. You don't have the dead time during two chunk computation. You see here at the end of the chunk, the thread start. Wait for some duration, and finally write on the disk. For the second transfer of chunk, a second thread is start, and so on. So we polarize the CPU file written and the GPU processing. So for this version, the bench it's around 13.5 seconds. The last improvement we can do is use, as we see at the beginning, the pained memory to optimize this part. And here it's possible to do the convolution for the both array in same time. To do that, so you can merge the two convolution with putting U and V above each other and separate with 3 rows of 0 and call one convolution. And after you must use slicing to retrieve the Laplacian for each image, for each array. So I give you the solution. So bind memory. This time I use a basic function bind alloc a pine memory and create a NumPy array from buffer a function. So now we have a frame a CPU with binded memory. For the merge of Laplacian of convolution, it's here. You define a big array, UV, with size two number of rows for each image, plus three rows. And you put with slicing each image at the top and at the bottom of the array. And for before call kernel, you retrieve the Laplacian at the top and bottom of array. And you write your image in a chunk buffer. To have efficient transfer, you must use memcopy in place of get method. And after it's the same code. So with this version, the bench is around 12 seconds. To run a version with processing and transfer in parallel, the gain will not be huge because your program is dominated by GPU calculation and disk writing. So why not to try? The difficulty is to write in buffer. To write on this, the buffer transfer asynchronously. It's possible to do this with using a stream dedicate method to call a function at the end of the stream with a large host function. You can see the documentation. It's a string class. And when the stream is finished, you can add a callback to call a function on GPU, on a CPU. So it's possible to do that. So conclusion, we have seen the main principle of CuPy. Porting program already written in NumPy and CuPy is quite easy. But the library remained open to feature close to CUDA feature like raw kernel, pine memory, stream, which allow to more refined use of GPU computing possibility. Thank you.